I hope that you will be able to hear me and also
Yes,
see
yes,
the screen.
yes, visible and audible.
So, uh, so today's last session on Friday. So, as per the request, we have changed the slot from Friday to Monday. So every Monday it is going to take place. And because so original slot was Tuesday. So from Tuesday we postponed it to Friday. Now we are preponing it to Monday. So that means today's session is the week three session, and week four session is going to be next Monday. That is today's Friday, 3 days from now. So next Monday is 19th. 19th we're going to start the sessions regularly on Mondays every week. And yeah, so if we continue this. Okay, so last week we had a question. Last week we were discussing the last question, and both you and me were not sure what the question was asking. So this was about almost percent.
Yes, almost two set problem.
So first, let's look at it. And then we will go to the three questions. So it will be only six questions. Even if we take 12 minutes per question or 15 minutes per question, we will be finishing well within time.
So
So
can you please check your audio connection because the voice is not clear to me. Probably there is some issue today with the audio system.
okay. Okay, so because there is no one else to verify this, I don't know what is the issue.
I think no one else is here.
Yes, so
Actually,
let's do. Shall I reconnect?
so this time you were clearly audible. Yeah, when you spoke that shall I reconnect, then you were audible
Okay,
clear.
so I'll hold the mic close to my mouth so that it's better. And even
Yes,
after that, okay, let's test this. And if you still face issues, then let me know. Then I'll try to reconnect.
so it would be better if you reconnect because it's still there is some issue in the voice. It is coming. Some lagging is there. I think.
Hello.
Yes.
Is this any better?
Yes. Slightly better. Yeah.
Okay, so I have connected my phone. Uh, so with this phone, I'm not able to turn on the camera. Uh, so if it is fine, I'll the camera turned off.
Yes, it's okay. And your voice is clear. Yeah.
Try to also connect the laptop and see camera can be accessed from here. I think the screen is still visible to you.
Yes, visible.
I'll show the question. So you can keep reading the question. So I'll try to fix the camera. So I have connected three devices. One for the camera, one for the audio, and one for the screen share. Let us test this. Primarily, the audio and screen share should work.
Yes. And even camera is working now.
Fine. So you asked this question that if 2SAT is already polynomial time solvable, then what question are we asking for the almost 2SAT problem?
Yes.
So here in this question, we had this 2SAT formula. So every clause had at most two literals, and from this 2SAT formula, additionally there was parameter k equals 1. So the almost 2SAT is asking that uh, can you cover sorry, can you satisfy all the clauses except one in this 2SAT formula? So your objection was I can uh, satisfy all the clauses. Was that the objection?
Yes, because I can verify, I can satisfy the entire Boolean formula, all the clauses in the polynomial time. So, and moreover, I was not clear about what this k is equal to 1 here is.
Oh, right. So there was a confusion in the video also. So in the video, it was saying something else. Uh, but I looked at the textbook and it was saying something else. So the textbook definition was that can we satisfy all the clauses except possibly k of them. So there are so many clauses. There are n variables and n clauses. So can you satisfy all but k clauses with some assignment? So you are allowed to not satisfy at most k clauses. That was the textbook definition. So that is the correct definition. So we will try to understand that why this problem is hard. So I will write down the definition once again, and then we'll look at an example, and that will make the understanding clear. There is an input formula, in a formula phi where every clause consists of at most two literals. And the question is, so additionally, there's an integer k is also part of the input. So the question is it possible uh, to satisfy uh, all but k clauses? Another way of putting the question is it possible to make phi satisfiable by deleting at most k clauses? All but here also should write that these two things are equivalent. These two questions, the question one and question two are equivalent. And then we got confused and we said, okay, no matter what user formula is given, we can find in polynomial time whether it is satisfiable or not. If it is satisfiable, we can find the assignment. But here the question is slightly different. For example, let me take an example in two variables. Let us take two variables x and y and all the possible two literal clauses. So x or y bar, x bar or y, and x bar or y bar. So now you know that no matter what assignment you give to x and y, one of the clauses will remain unsatisfied. So this formula phi in x and y is not satisfiable. But we can verify that in polynomial time. And if it is not satisfiable, then it will give an additional parameter k equals 1. And then you would ask that can you satisfy all but one clause? Then you can say, okay, this is a valid question to ask. Does it make sense?
Yes, yes. Yeah. So my intuition here is that say if I consider all the clauses and if the final value of phi comes out to be zero, say the formula is not satisfiable, and quite possible that if I remove one or the at most one clause, then the entire formula after the removal of the one clause may turn out to be satisfiable. And now the real problem is identifying that clause, and which is creating conflict with the other existing clauses.
Yes. So first question is, as you said correctly, how to identify these clauses or whether we can identify at most k clauses that are causing the conflicts. It may happen that more than k clauses are not satisfiable. In that case, we have to say no. So again, this problem is not easy. So this is NP hard. So to decide that whether it's possible to satisfy uh, all but k clauses, to answer that question is not easy because that transformation to implication graph, that machinery will not work anymore.
Yes, uh, and I could remember an analogy of this, even though I do not correctly remember the name, but it is minimum spanning tree and the Steiner tree kind of the thing. So in the minimum spanning tree, we have to cover, to find the acyclic subset of the edges connecting all the vertices, and whereas in the Steiner tree, we have to connect a subset of the vertices. So getting the MST is pretty easy, but getting that subset of the thing becomes NP hard. Yeah.
Correct. So you have good analogy. So yeah, so as soon as uh, you you introduce additional restrictions, the easiness, the reason a problem is easy, that reason may not remain valid anymore, and that will make the problem difficult.
Yes. Yes.
So now at least we understand. Even I was not aware of almost two set problem and its hardness, but now we have a fair understanding of why the problem is worth studying. So this was from last week. So maybe 6:30. Let's move to this week. A couple of questions only, and you have watched the videos, it will be very fast. Otherwise, it will take slightly more time. Uh, yes. True, false. Actually, answers are also given, but we'll just argue about it. Uh, I will copy this. Uh, copy that. Okay. Copy. Uh, 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 pasted, but not in a very nice way. Okay, so this is good enough for our purposes. So we have these four statements. So which of them are true and which of them are false? I'll go to
Yeah, so if a graph has vertex cover of the size at most k, then any subgraph of G has a vertex cover of the size. So uh, if I can cover all the edges of the graph with at most k vertices, uh, then any subgraph can also be covered with at most k number of the vertices. So that seems
yes,
true.
yes, because there, there is already a vertex cover of size at most k, which is capable of covering all the edges. Now, any subgraph of G has only a subset of the edges. The subset of the edges will also be covered in it. So now the question is, what is that vertex cover? That vertex cover would be a subset of the original vertex cover, and because it's a subset of the original vertex cover, therefore its size would also be at most k.
Yes, yes.
To be more precise, let us say uh, uh, the subgraph is denoted by H. H is the subgraph of G. And now let us say that there is a vertex cover of size at most k. Uh, we denoted, let us say we denoted by S. The S is a subset of the vertices. So you consider the vertex of the subgraph S and take those vertices which are part of S. So this is going to be a vertex cover for the subgraph.
Yes, yes,
And therefore this its cardinality is also at most the cardinality of S, and therefore the statement that the vertex cover of the subgraph is also of size at most base 2.
yes, yes. And second one, if a graph G has a vertex cover of the size at most k, then any induced subgraph of. So what this induced subgraph is?
So induced subgraph means you take a subset S of the vertices and you have to connect all the original edges among the vertices of S. So for example, let us say this is the whole graph and you have picked some of the vertices. So let us say this is a subset S of the vertex set. There are some other vertices outside. Now, if there is an edge between two vertices in S, you also have to pick. That is, you the as soon as you have picked the set S, that induces the edges because the induction is directly from the original graph. So, for example, suppose there was an edge here and you did not pick it, that is not allowed.
Oh, okay. So in this case, it need not to be true because quite possible that that edge might be getting covered by some of the vertices outside this inner circle, and which are no longer the part of the subgraph, the induced subgraph. So, but the question is asking about probably the number of. So has a vertex cover of the size at most k. So yeah, so uh, now that uh,
I will restate the definition of what is induced subgraph. And so, what there's something called subgraph and there is something called induced subgraph. Let us all be very clear on what these two things are. So let us take an example, very small example. This is a large example. That is why you got confused. It's still a very small example. So let us say that I have a graph which is this much. So two triangles. Let's number the vertices. So if I choose the subset 1, 2, 3 of vertices, then the subgraph induced by S is this triangle 1, 2, 3. So that means because I have chosen this vertex set S will induce a subgraph where all the original edges among the vertices of S should be present. Now, on the other hand, if somebody had chosen this, let's take a different color. I think somebody can choose 1, 2, and 2, 3 as two edges and declare it as a subgraph. That is fine. Okay, so these two green edges is a valid subgraph of the graph. That is the G, but it is not an induced subgraph. Now, we have already concluded that for a subgraph, the vertex cover size cannot exceed the vertex cover of the original graph. Now, what happens for an induced subgraph? So, what is an induced subgraph? It is nothing but, let us take this color. An induced subgraph is nothing but the subgraph induced by a subset of the vertices. So, therefore, it is also a subgraph of the original graph. So, now if you do the same reasoning, let us say instead of subgraph I write let H, I'll write it again. So let H be an induced subgraph of G let us say induced by a subset S of the vertex of G. Then S we have used already for vertex cover. So this subset is not S, so this has T. So T is a subset of vertex that induces the subgraph, and S is the vertex cover for the original graph. Then take all those vertices in S that are in the induced subgraph. So my question is S intersection T a vertex cover for this induced subgraph? If yes, then the cardinality of S intersection T is also at most K, because S, the original vertex cover, had size at most K.
Yes, so yes, so the answer is yes, because if S intersection T a vertex cover, so T, since T is a subset of the set of the vertices, uh, and so yeah, so it shows that those vertices would definitely be covering those edges which are induced from the original graph, because the edge then will the only thing is that so my answer is yes. Yes, S intersection T would be a vertex cover of the edge. Yes, this is okay. And I'm little doubtful about the cardinality of this thing. Uh, so what the cardinality be?
I can. You are partially convinced that uh, the answer is true. So let's try to convince ourselves fully. So I am looking at any induced subgraph. Now the induced subgraph is due to some subset of the vertices. Let us say 1, 2, 3. These three vertices in this graph induces this subgraph. Now I want to ask that, okay, in this induced subgraph, what is the vertex cover? Now I claim that from the original vertex cover. So in this case, what will be a vertex cover? Let us say in this original graph, I am going to mark the vertices of the vertex cover. So in this graph, can you mark the vertices of a vertex cover?
Okay, so vertex number 1 and the vertex number 3.
Correct. So my claim is that if you take the intersection of this original vertex cover, which I am denoting by S, with T, that is definitely going to be a vertex cover of the induced subgraph as well. So in this case, 1 and 3 is also going to cover all the edges in this triangle. Why is that so? Because if you look within the induced subgraph, take any edge. Okay, that edge is being covered by either of its endpoints. Now both the endpoints are within the induced subgraph. So now you have to pick vertices from within the subgraph to cover the edges of the subgraph. And you know that because the original vertex cover S has a subset which must cover all the edges within the subgraph also, and this subset is nothing but S intersection T, because something which is outside of T, outside of this inducing subset of vertices cannot cover any edge within the subgraph. So S intersection tree must be a valid vertex cover for the induced subgraph edge, because a vertex from outside is not capable of covering any edge inside the subgraph.
Yes, and what about the cardinality of the this intersection of S and T? This will definitely be smaller than K.
It will be at most smaller, at most the cardinality of S. So the cardinality of A intersection B must be at most cardinality of A, or we can also write it must be at most cardinality of B. Now we know that cardinality of S is K, that there is an original vertex cover of size at most K. So any subset of the original vertex cover is also of size at most K.
Yes, yes. So it's true.
So it is like that. The third one is about independent set.
So if a graph G has an independent set of the size at least K, if G has an independent set of the size at least K, then any subgraph of G has an independent set of the size at least K. So K is the number of the vertices in which no vertex is connected to any other vertex.
Yes,
If I take its subgraph, then quite possible that this if it is at least k, so there are at least say three vertices and none of them is connected, and if I take subset, so would be at least this at least thing would be maintained or not for the subgraph. So the thing is that would be at least three. It could be at least no. So this at least thing won't work for the subgraph. No, it won't work. Yeah. So therefore, this is false. Yeah.
yes. So what is a subgraph? A subgraph is any subset of the edges. Now, if you choose only one edge from the graph, that is also a valid subgraph. Now, if you have chosen only one edge, then what is the uh, independent set size?
So there won't be any vertex, no zero.
No, so, I mean, suppose you have a graph which is composed of only one edge, then I'm asking that this is vertex u, this is vertex u. So, can we say that u is an independent set?
Yes. U is an independent set, and so is V. So is V. V is V alone. V alone.
V alone is an independent set because it is not connected to anything else in the independent set.
Yes,
Uh,
yes,
so there could be a subgraph consisting of only one edge whose independent set size is only one vertex, whereas the graph could have very large independent set number. So if you insist that I want every subset to have a very large independent set, that is not true.
yes,
So remember what is a feedback vertex set.
yes.
So
So yeah, we have to find the maximum number of minimum number of the vertices whose removal will make the entire thing acyclic. We'll remove the cycles from the graph.
yes, it is the cycle killer. So removing a subset should make sure that the graph has become a forest. That is a set of trees. So similar reasoning. Uh, so you know that there is a graph whose feedback vertex set has size at most k. Then you look at a subgraph. Will not be induced, but a subgraph. Can we say something about its feedback vertex set?
Oh yes, so since if I use at most k number of the vertices, then if I can kill the cycles, and if I take the subgraph of the G, then obviously clearly with the k number of the vertices, I would be able to kill cycles if at all, if those cycles are there in the subgraph. So it is
Yes.
true, seems to be true.
Since all the cycles are killed in the original graph, in the subgraph also the cycles will get killed.
Yes.
So we can discuss one question. So before the break, let's discuss one more question. It is actually the question requires some. I will just give you the context of this. I will let you read it from here only. So if you're looking at question number 2.
So suppose we have an algorithm with runtime this for disjoint compression feedback vertex set. Okay, so what this disjoint this thing is this compression feedback.
Yes. So we have understood what is feedback vertex set. It is a subset of the vertices whose removal uh, will kill all the cycles, will make it a forest. Now uh, there is a special variant of the feedback vertex set which is called the disjoint compression feedback vertex set, and there is a way to solve the feedback vertex set by solving that special variant. Okay, so I will define the special variant, but the question is if that special variant can be solved in order n to the k times n squared time, then using that algorithm, the original feedback vertex set can be solved in how much? So first the options are that question. Oh, the option 2 and 3 are same, right?
So yeah, uh, so you were not clearly audible when you explained the meaning of the term disjoint compression feedback thing. I could only hear till that point when you repeat the definition of the feedback vertex set, cycle killer, and after that you told something, so that was not audible.
Okay, is it clarity issue? Audio is not clear.
It is okay now. Now the audio is okay.
Okay, so let us understand the definition of this spatial variant called uh, disjoint compression FBS. So as usual, you are given as part of input a graph G, a parameter K, and a subset S of the vertices of the graph uh, such that S is a feedback vertex set of G and S has at most K vertex, K plus 1 vertex. So you are given additionally. So generally in the feedback vertex set, you are given two parameters, the graph and K, that is whether there exists a set of K vertices whose removal will make the graph a cyclic forest. Additionally, you are given a K plus 1 sized, at most K plus 1 sized feedback vertex. So you want to get from here, you want to compress this K plus 1 to K. You want to get a smaller feedback vertex. So what is the question we are asking? So the question is, does G have a feedback vertex set F of size at most K, smaller size? Okay, you understand?
Yes. So yeah. So but we have to find a subset of the vertices as well, such that the size of the S is k plus 1. So in fact, but then this question is a simple question, that does G have a feedback vertex set of the size less than or equals to k, and where is the similarity in between this thing, a simple feedback, and this disjoint compression thing?
So the input is saying that, look, I give you a graph, and I also tell you that this graph has a feedback vertex set of size k plus 1, at most k plus 1. So he is telling that, look, it is possible, it is fact that k plus 1 vertices can be removed to delete all the cycles, to kill all the cycles. But can you give me a smaller feedback vertex? Okay. Can you give me k vertices whose removal will also make it afford it?
Okay, okay, yes, yes. So I have to find that one vertex, one important vertex, and which is not that important, and which can still be removed. And yeah, so
Right.
okay.
But there is one more thing which I didn't tell you for the sake of simplicity. Additionally, there is one more constraint that you want that the you have been given a feedback vertex set of size k plus 1, which is denoted by S. So you want that the new feedback vertex that you get, which is F, these two things should be disjoint. Yeah, okay, so these two things should be disjoint. So that is the origin of the name disjoint. So this word disjoint is coming for this reason. So of course you are given a larger feedback vertex set. You want a smaller feedback vertex set. At the same time, you want this feedback vertex set to have no common vertices with the given feedback vertex. So that is the definition. It's slightly complicated.
Yes, yes. Yeah, yes. So the minimum number of the vertices in the graph in that case should be equals to 2k plus 1 for a partition thing.
Okay.
Otherwise, yeah, such a disjoint thing won't be feasible.
So now uh, there is a way to solve the original problem and find the solution to the feedback vertex set problem by solving the spatial variant. So this can be solved by using solution to, so the spatial variant I'm going to call it DC for disjoint compression feedback vertex. Okay. So if someone solves this special variant, there is a way to solve the original variant. Okay. Now we are looking at this. The question is saying that suppose you know that the spatial variant, disjoint compression feedback vertex, can be solved in 2 to the k n squared running time. Then for the original problem, that is the feedback vertex problem, how much time is required? All right.
So what did you say that for the original thing?
I'm looking at option 1.
Yes.
There exists an algorithm with runtime this much for feedback vertex set. That is the original problem. Uh, so
Yes. So disjoint compression thing is having running time this, and without, so it shows that we should have the second set as well, and whose cardinality would be one smaller than this. But this is a smaller one, I think. So k plus 1, and then yeah. So there exists an algorithm with the running time of this for the feedback vertex set. If the disjoint is taking this much time, so 2 raised to the power k plus 1. I don't know if I take.
It is quite tricky. Uh, it is not easy to, I mean, you can only guess, but to compute this, you have to understand the algorithm, that how this spatial variant can be used to solve the original problem. Okay. So I think this will itself take more time than necessary. Uh, are you interested in knowing the algorithm, or I will just tell you the formula?
So better if you show that write up again, which wherein you explain this digital compression thing, and you made a last statement, that is the feedback vertex set can be solved by using the solution. So digitally disjoint compression feedback vertex set. So yeah, so S is k plus 1, and then F would be of k. So yes, uh, yeah. So what's the meaning of this statement, that the feedback vertex set can be solved by using the solution to the disjoint thing?
All right, all right. Okay, so then I will tell you how, what is the meaning of this statement. Okay, so before that, there is one more variant we have to understand, because there are two parts to the algorithm. Okay, so let's look at another variant, which is simply this part, compression feedback vertex. So uh, disjointness is not uh, imposed. So there's a variant which is called the compression feedback vertex. Let me turn it up so you can see it together. So here again, the input is uh, same. You have a graph G, parameter K, and additionally a feedback vertex set of size at most K plus. Same input, same input as disjoint compression feedback vertex. But the expectation is that you will output a feedback vertex set of size at most K, and there is no disjointness condition. So what I said initially, does there exist a feedback vertex set of one smaller size? That much is the requirement. Okay. So now we will see that how to use. So there are two steps. First, we will solve this problem. Uh, so I am going to write the same thing, that this variant compression feedback vertex set can be solved using the variant of the disjoint compression feedback vertex. Can be solved by using a solution to the disjoint compression feedback vertex set. Okay, now we'll see how it. The first step is to solve this, and from here we have to go to the original problem. So it is like, first you solve this guy, which will give you this guy, and then you go to the vertex. That is the flow.
Yes, but the I mean, this is straightforward, because if we can find two things, say k plus 1 and k, which are disjoint, and from the k plus 1, if I can find k, so then clearly, I mean, the existence of the solution of this DC will imply the existence of the solution of the compression feedback thing.
So
Because
yes,
in case of the DC, we need to have 2k plus 1 number of the vertices at least, And whereas in the case of the compression feedback, the k plus one number of the vertices are sufficient. And out of those k plus one, I can reduce it to the k, and both need not to be disjoint.
Yes, so somehow is where there is a scope for innovation. But how do you get a feedback vertex which is slightly smaller?
So a smaller thing exists because we have a solution of the DC feedback. Because the solution of the DC feedback implies that we have k plus one set k plus one, and the other set k. And we are only in the search of k only. And so therefore, yeah, existence of DC implies the existence of the compression. Compression means k that to, oh, I see, okay. So there is some issue because if k plus one exists, then how to ensure that that k plus one only can be reduced by an amount of one, and so that is problematic. Individually, I have two sets, k plus one and then k, but to ensure that k plus one can be reduced to k is problematic. Yes.
Correct. So I'll give you the high level idea. So it is a schematic. I think if you remember the schematic, that should be sufficient. So so you know that your part of input is a larger feedback vertex. Okay. So let us say you have a large graph out of which k plus one vertices are given to you, which is the feedback vertex. So we are calling it S, right? So S is the feedback vertex. So let us say this is S. And now the rest of the vertices, there are some other vertices in the graph. Uh, these so the graph formed by the rest of the vertices, this is a forest. Okay, so once you have deleted the feedback vertex set and the edges incident to the feedback vertex set, you have the remaining graph, which is a forest. That is by definition. So now you want to compress this k plus 1 to k, and what liberty you have is you can take some of the vertices from here for the formation of the smaller LPS. But if you take all the k, so if you drop one vertex only from this, then you will get a k set, but that need not be a feedback vertex. That is the problem. Okay. So it may happen that you are taking some vertices from here and some vertices from here, and these two together is a feedback vertex set of size at most k. Okay.
Yes. Yes.
So now, in how many ways you can choose uh, uh, k or less vertices from the feedback vertex? So let us say you have k plus 1 vertices in the given feedback vertex set. You are going to choose some I vertices uh, from here, some I from here. So rest remaining n minus I you are picking from here. Okay. So there are k plus 1 choose I ways of picking I vertices from the given feedback vertex. But I can run from where to where. You may not pick anything at all from the given feedback vertex set, and at the most you will pick k vertices from the feedback vertices. So this is the total number of choices you have for picking a subset from the given feedback vertex. Does this make sense?
Mhm. Yes. So
This is
yes.
the argument that your target is to get a k-sized feedback vertices set from slightly larger feedback vertices So you have made a plan that I'll pick some of the vertices from the given feedback vertex set and the rest of the vertices from outside. So those vertices you are picking from the feedback vertex set can be picked in so many ways. K plus 1 choose I can go from 0 to k.
Yes, but yeah, it's true. But then, don't we need to take the other combination as well, wherein we would be selecting the remaining elements from the second set?
Yes, that is the second part. You're right. So how do we choose the rest of the so that is where we are going to call this. So if we know there is an algorithm for the disjoint compression feedback vertex set, then we can use that for obtaining the rest of this. So this n minus I vertices will be obtained by saying that okay, I am going to pick I'm going to pick I vertices from here, and now you solve the disjoint compression feedback vertex set by picking vertices which are not here. So disjoint from this. So I will mark this red. So I vertices you have picked. The rest of the vertices inside the feedback vertices you don't want to pick at all. Okay, so you know for a fact that this together is a feedback vertex set of size k plus 1, and then you give this additional constraint that okay, I don't want you to pick any of the vertices here. You give me n minus I size feedback vertex set for the remaining. So that is where you are going to use this algorithm. And so if this algorithm takes time t, some time t, so multiplied by t time will be required for your overall this algorithm for compression feedback vertex. So t is already given to you in the question, and then we will put it here. So that is the overall plan. I just said at a high level. If you read, watch the video, it will become clearer.
Yes, yes. So, I mean, after this summation, and then we are multiplying it by t, and what this t here stands for? This is the running time for which algorithm?
This is here that suppose we have an algorithm running in 2 to the k n squared time for disjoint compression feedback vertex. This is given. This t is given to you. Okay. So 2 to the k into n squared. That is t.
That is t. Yeah, right. So, yeah, and k plus 1. So what is the order of this? I mean, what is the solution of the summation?
Yes. Now we will put this. I'm not, let's remember this runtime. So this runtime is for obtaining a k size disjoint compression vertex feedback vertex set 2 to the k n square time is required. Okay, let's remember this.
Yes,
So now instead of t, I'm going to put this value. I'm going to replace t. So 2 to the k n squared. But then I'm not looking for k size disjoint vertex set. I'm looking for only uh, oh, k minus. I'm interested in obtaining this much from the remaining. So this k minus I. So the other I have already picked by using this uh, choices. So I have made an arbitrary choice of I elements out of k plus 1 already. So the remaining k minus I want to choose using this algorithm. So here the parameter will be updated to k minus I instead of k. And now you can apply binomial theorem. Now this will come
yes.
out 2 plus 1 to the power k. I want to get a k size. Yeah, I mean somehow of 2 plus 1, but let's not worry about it too much. So this is order, and so this much time will be required. Let's see whether it matches or not. 3 to the k n squared. So the first uh, the last option. The last option says 3 to the k n squared for the compression feedback particle. So we have only solved the compression feedback particle. We have gotten down from k plus 1 to k. Okay.
Yes.
So that's how the option B is correct. Now I will not. So there is another way to go from compression feedback protected to the original problem, that is feedback protected. But I'll just tell you the formula. So the option 2 and 3 are same. That's what I realized now.
So option there is a difference. In option 2, there exists no algorithm with the runtime, and in option 3, there exists an algorithm with the runtime.
Correct. Sorry. So,
Yeah.
so let us say we want to decide between A and C now, that whether A is correct or C is correct. The difference is there's a 2 to
So,
the and there's a 3 to the k.
yes, so they are multiplying things by n instead of n square, multiplying it by n cube. It gives me an impression that as if I am calling this disjoint compression n number of the times somehow
Yes,
to get the feedback vertex set. That kind of feeling.
yes. So there's an algorithm that runs at most n times this disjoint compression feedback vertex, and therefore the runtime blows up by a factor of n. So it becomes uh, okay. They are saying that the answer is option A is correct. That's what they're saying.
So their answer is there exists an algorithm with runtime 3 raised to the power k. Oh, there is one more option, option number one. Wherein, so basically it means that yeah, we are calling this compression feedback n number of the times.
Right. For yeah, that is correct. So option D is correct because its compression feedback is solvable in k to the k n squared time. Now this is repeated n times, and that is how the original feedback vertex set will take 3 to the k to n cube time.
Yes.
So I think we can take a break now. We're pretty tired. Uh, what do you want to do? We have many questions to discuss, but I think we'll not discuss everything. It is not necessary to exhaust ourselves and discuss everything. Let us take this break till 7:30, and then we will finish quickly by addressing two more questions. Is that fine?
Yes, perfectly fine.
Okay, fine. Let's then meet at 7:30.
Sure.
Am I audible?
Yes, yes, audible.
Okay. Uh, so did you get a chance to read the third question?
So, which of the following statements are true? A directed graph with a unique topological order is a tournament. So actually, I don't know this two terms here. First, topological order, and the second one is tournament.
Okay, let's look at these. Uh, so tournament is easy to remember. So suppose there's a cricket match going on, not a cricket match, a tournament going on. So there are three teams which are participating. So team A, team B, and team C. So you want every team to play every other team. So there should be a match between every pair of teams. Okay. And then there will be one outcome. So if A defeats B, then we will draw an edge directed from A to B. Okay. If, and so on. So we will have to draw so many edges. Basically, we will draw a clique. We'll draw a clique, and every edge uh, will have a direction. Okay. And if A defeats B, then B cannot defeat A. So the direction is unique between any two vertices. That is the definition. So such kind of a directed graph is called a tournament, where between every pair of vertices there is a directed edge, and I think that's pretty much it. Let me also verify if I should do correct.
And do we consider transitivity here? Like say A defeats B and C defeats B, A defeats B and C defeats B. So I mean, no transitivity, nothing, no transitivity can be implied from the directed graph. Is this?
Let me check.
Okay.
So there should not be any loops. So in this case, there is no loop. So in a tournament, the directed graph, there are no loops and exactly one edge between every pair of vertices in either direction. So what you were saying, if there is a loop in situation will look like this. Uh, A defeats B, so that means A is a stronger team than B. And B defeats C, that means B is even stronger. So C is the weakest. So C should not be able to defeat A. So yeah, so some transitivity must be this thing maintained. So yeah, one more property which I did not tell you is that the directed graph should have no loop,
Yes, yes.
not a loop.
Hmm.
Or
And what about topological that stuff?
topological order in a graph is de- defined in a directed graph. So I will give you an example. So let us start with a simple example. Let's say four vertices. So A is directed to, so there's a directed edge from A to B. There's a directed edge from A to C, and then there is a fourth directed edge. So I will say that A, comma B, comma C, comma D is a topological order if uh, We don't want edges from something that is coming later to something that has. So edges have to be directed. So let me introduce some terminology. So we'll say that if if B appears later than A in the order, then B is a successor to A. Okay, then we do not want, and other way A is a predecessor and A is the predecessor to B. So all the edges should be directed from predecessor to successor. So that means in this figure, ABCD is a valid topological order. At the same time, ACBD is also a valid topological order.
So if B appears later than A in the order, then B is a successor of A, and A is a procedure of to B. Okay. Yes. So A, B, and how come this C came in between A to B? Okay. And what about this BC then? There is no relation in between B and C.
So B and C are sort of at the same level. So you can say that you can see that A is the predecessor to both B and C, but these two are not really.
Mm-hmm.
So it's sort of like so this is a grandfather. Uh, this is the uh, child level. This is parent level, and this is grandparent level. So there is a better definition. I think this is what I told from my memory. The better definition of topological ordering is following. So it is an ordering. Let's use a different color. So this is a more precise definition. What I said is intuitive, but what is written here is more precise. So an ordering of the node of the graph where every node appears after all the nodes pointing to it have appeared. Or rather, I'll say all its parents. Let's not produce more terminology. Let's just say all the nodes pointing to it have appeared. This precise definition. So therefore, since A is pointing to B, so A must appear before B. A also should appear before C. Since B and C are not pointing to each other, there is no ordering which is defined between B and C. So B and C can shuffle among themselves, but A must appear before both B and C. And on the other hand, since D is being pointed to by B and C, so D must appear after B and C.
Yes, yes.
This is topological ordering definition, and this is the tournament. Tournament has two things: should not have loops, and there should be one directed edge between every pair of vertices.
Yes.
Now we will look at question number 3.
So a directed graph with a unique topological order is a tournament. So if the topological order is unique, so it shows that there are no vertices like B and C, and connectivity is there, definite connectivity is there in between the vertices. And if the definite connectivity is there in the vertices, and moreover, a cycle cannot exist in the topological order, and neither this cycle exists in a tournament also. So therefore, yeah, this is true. This is true that a directed graph with a unique topological order is a tournament.
Let me
Yeah,
take it to the whiteboard. But, uh, select all the things. Select all. Oops, right, I'll just uh, take it to good enough. This for our purposes now.
again, a slight audio issue.
Okay. Uh,
Yes.
I think whenever I'm moving away from the mic, I think I have to change this mic. Alright. So I'm going to keep it close to my mouth. This is better.
Yes, yes, perfectly fine.
All right. So we are looking at the first statement that if you have a directed graph with a unique topological ordering, then it must be a tournament. Okay. So can you think of a directed graph which has a unique topological order, but at least fails to have one of these properties? One property is there must exist. So in a tournament, there are two properties. Must exist a directed edge between every pair of vertices. That is one property. The other property is must not have a loop. So that means there should be a ordering of who is strong, who is weak. Should not happen. The weak team beats a stronger team. So is it necessary that in a directed graph with a unique topological order, the first property is definitely true?
So must exist a directed edge between every pair of the vertices. Yes. Otherwise, we would be having those B and C kind of the vertices, and they can always be shuffled. So, like, uh, but it is not necessary because quite possible that
So you're
uh,
talking example. Even in this example, this edge is missing. So this example is not a tournament. At the same time, it does not have a unique topological order. All right.
yes.
Now the question is, do you have a graph where there is a unique topological order, but it fails to qualify as a tournament?
So yeah,
So how about this graph in three vertices? A is directed to B, B is directed to C. Does it have a unique topological order?
Yes.
A followed by B followed by C. There is no confusion about that because that is the natural successor predecessor relationship. So it is a valid, unique topological ordering for this graph. But on the other hand, whether A is able to beat C, what is the relationship between A and C, that is not specified at all. It does not qualify as a tournament. In a tournament, we must know that what is the relative power or strength of every pair of vertices. There should be an edge between them.
Yes. 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 So yeah, this is false. And the second, a tournament has a unique topological order. So if I have a uh, tournament here, like if I connect this, I mean an agent between A and C. Then this won't be having a unique topological order. Why so? Because yes. um
So, what is the direction of the edge between A and C? A to C or C to A?
So from A to C, because for a tournament the loop cannot exist.
Yes, yes, you're right. So, you have given an example where there is what is the topological order? Is there a topological order here?
So topological order, like say A, and then so when A finishes, then B and C both can finish. So it could be A, B, C, or A, C, B. I think both will work. No, 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 no. But then there is an edge from B to C, so C will finish at the end. So yeah, so ABC is the topological order, and
C
so
must appear after all the vertices pointing to it have appeared. So,
yes, yes, this is unique in this case. Uh, but yeah, so it is unique, but a tournament has a unique. So if something is tournament, if something is tournament, uh, if something is tournament, then can we have a non-unique topological order? So to have a non-unique topological order, I mean. So yes, that can happen. That can happen. Like say, if I introduce one more vertex here, D, so then A to D and then D to C. Uh, but then I have to add A to C as well. And if I add A to C, so yes, so if I add one more vertex here, D, say from A to D and then D to C, and I connect A to C as well.
so there is a new vertex. How are you connecting this?
So A is connected to D and D is connected to C. So now in this, I do not have a unique topological order. Like say it could be A, B.
Tournament first. So every pair of vertices must be connected with an edge. So you have to define the edge between B and D as well.
I see. Yes, yes. So that has to be there. And if it is there, so then the things will become unique automatically. Tournament has a unique topological order.
So let's look at the option. Accepted answer is uh, an acyclic tournament has a unique topological order. Oh, so what was the definition of tournament that I told you? That there must not be a loop, so it should be acyclic. So there, okay. So there are two definitions. So the way they are looking at it, a tournament should have only one property. that between every pair of vertices, we should give a directed edge. Now, the additional property which I said, that it should not have loops or cycles, that they are calling a cyclic tournament. So they are allowing cycles in a tournament in the definition, whereas the source where I'm looking from, they are not allowing that.
Okay. So then, obviously, so whatever we discussed so far was in fact true for the acyclic tournament only. And just now we have seen that the acyclic tournament has a unique topological order because it does not form a cycle, and moreover, there would be a directed edge and would be in any pair of the vertices. So clearly, this option is correct.
Yes. So we have to rule out B and C. Uh, so is it true that so now think of tournament as having this one property on that you have assigned a directed edge between every pair of particles. Now, can you think of a tournament which does not have a unique topological order?
So now, if loops are allowed,
Yes,
so
the figure. Loops
yeah,
are
so
allowed.
now topological order may not be unique.
Correct. Like if, for example, if I consider this ABC example, I allow a loop.
Yes,
So the loop has to go from, I mean, the edge from uh,
C
C
to
to
A.
A. So now this has become a loop. So what is the topological order? Cannot even exist because we are saying that vertex A must appear after C. On the other hand, we are saying that uh, B should appear after A and C should appear after B. So by transitivity, C should appear after A, whereas this edge is saying that A should appear after C. So this is self-contradictory. So therefore, a topological order will not be possible if there is a loop.
Yes. So here, topological order is not possible.
Therefore, we can rule out uh, a tournament has at least one topological order. That is not done. It may not have. So therefore, uh, uh, if it does not have any topological order, the question of unique topological order also does not arise. Uh, and this first is already ruled out. So this example for option for A for first. Alright, so this is true. This is true that these are
Yes.
cycles, so it is acyclic tournament. Then what happens? There is at least one source particle. So the more formal way of proving is that because the tournament is acyclic, there is at least one particle which is not having any predecessor, which is the source, because everything starts from here. Okay. So formal way of proving for is that there must exist a source vertex in uh, a cyclic in an acyclic tournament. So now if somebody can say why one source vertex? Can there exist multiple source vertices in an acyclic tournament? Or is it that's a valid question. Can there exist multiple, what is the source?
So yes,
That
so the source.
yes, go ahead.
No, but then in what been every pair of the vertices there should be connectivity, and so from the source all other I mean all edges are emanating and reaching to the sink kind of a thing,
If there are,
because it does not form a cycle.
yes, if there are multiple source vertices, then what is the directed edge between them? There is one, and that will disqualify one of these two from becoming a source vertex. Vertex.
So
So that means there is a unique source vertex in an acyclic tournament, and therefore it follows that there should be an unique topological ordering inductively.
so this was not actually clearly audible, but I think if we consider one more, it seems that so what is the definition of the source here? Source is the vertex from where all the edges, I mean, we have all the outgoing edges and no incoming edge. Is the definition of the source?
Yes.
Okay, so no incoming. So then there would be a single source and single source, uh, single source. And why so? Because for every other vertex there would be an incoming and an outgoing thing, and it is only for the, so this is somewhat similar to that uh, Euler's thing, wherein we used to say that there could be exact two vertices of the odd degree to have the Euler's path.
Oh
We
yeah.
started,
Yes. Because sum of degrees is even, then the number of odd degree vertices should be even. That's what you.
yes, video and audio. I mean, is your video got freezed? I think. No, no, it's fine.
I think there are multiple issues today. I don't know why it's like this. But I hope it is clear in your mind that in an acyclic tournament, multiple source vertices cannot take.
Yes, yes.
Okay, okay. I see. We are almost 20 seconds for the clock. So I think we can finish it here. And please note that next session is on this Monday, that is the coming Monday, and subsequent sessions are also scheduled on coming Mondays, every Mondays.
Uh, will it be possible for you to tell the topic of the next problem solving session so that yeah.
You must be part of this course. Last time we were part of. Let's look at. So we are going to look at this assignment 4 of randomized algorithm. Yeah. So it says that the topics are this: introduction to randomized algorithms via a simple randomized algorithm. So for every edge feedback vertex set, there is a randomized algorithm, and there are a couple of other topics like color coding for longest path, chromatic coding for feedback art. So some randomized things will be the topic of uh, next week.
Okay, yeah, yeah, fine.
Thank you so much for coming up with another.
Thank you so much. Yeah, thanks.
Thanks.
Thank you so much. Yeah, good night.